pounds. Volume times volume times 50 times x equals s squared times delta x. And then x is 0. S is 706. When x is 471, s is 0. The change is and then s. So I'm starting to do the problem here. So we have this relationship between height of your typical layer and side length of the square kind of pallet or wafer that we're going to find the volume and the weight of. So when x is 0, we need to get 706. And when x is 471, we need to get 0. So I think this does that. When x is 0, I get 706. When x is 471, I get 0. So there's my relationship between s and x, making my volume equal to that thing squared. I'm only want to write it once, so we'll write it over here. So the volume is going to be the negative 706 over 471 x plus 706. That's s. In terms of x, times the 150, that will give me the weight of the layer at x feet up. So right there, that's the force, or the weight of the layer at x feet up. And then force times distance, the distance that thing has to go is x. Oh, wait, that's not right. What did I miss? That's just area, right? Volume, right? Volume times delta x. That's my volume. I need the delta x to be the little height of the layer. And then times my density gives me the weight or the force of that layer. I'm going to move that a distance of x. So I'm going to integrate that thing from 0 to 471. So that's our setup work for the work of a typical layer in the pyramid. And so then I'm going to, how can I get a total amount of work if the work varies as soon as I move up a little bit? How can I get the total amount of work? How is it possible if the work varies as soon as I move up a little bit? If you haven't learned this yet, learn it now. We've been doing it all semester. It's going to be the sum of little bits of work. How can I get the total force on a plate submerged in the water if the force is varying on the plate? That's number 2. Total force is force varies as soon as I move somewhere else on the plate. How can I then get the total force on the plate? The sum of little bits of force. That's number 2. The sum. If you haven't learned, here's your day. Leap year. Leap day is your day to learn what an integral is about. If the force varies as soon as you move, then to get the total amount of force, we need an integral. We need to sum up little bits of force, and that will give us the total force. And that's what we do. That's what an integral is about. Anyone truly born on leap year? Anyone? There's a chance with a big group like this. Oh, okay. No. Happy leap year. Question? Because we got pounds. It's weight already. When you're in, so this is true for all these physics problems. If you're in metric and you're given kilograms, you need to get weight. Kilograms is not weight. Newtons is weight. You need force. Newtons is force or weight. But in English, pounds is already force or weight. You don't need mg or ma. Pounds is already weight force. So your 150 pounds per foot cube is what you need. That's 150 pounds force per volume. So there's none. So that's been true about all these problems. Yeah. We haven't used it. I just gave it to you, but we haven't used that. We would use it if we were working. If I gave you the mass in slugs in English units, but we never did that. So yeah. I just mentioned it, but we don't use it. But I did emphasize that in English units, you have a fast track to weight force. You don't need that conversion from mass to force. Other questions? So this is just going to be this right here. So in terms of grading it, so that's kind of, to do that by hand is a little ugly. You got to multiply that out. You'll have three terms, and then you're going to multiply each term by 150x. So you have three. That's not terrible, but it's not fun, right? So, but that's very manageable. So you're going to multiply that out, multiply each term by 150x, and then you have three terms of a polynomial. So that's manageable, just a little bit ugly numbers. But we'll just grade this on your setup, okay? We'll just grade this on your setup. How many foot-pounds was it? Anybody think they got the answer right?
1.3 times 10 to the 12.
1.3 times 10 to the 12? Anyone get that? Something like that? Someone else get something like that? A little bit of work or a lot? Yeah, you got that too? A little bit of work or a lot of work? What is that? A million is to the sixth, right? So billion. 1.3 trillion foot-pounds. Those Egyptians. All right. Questions on the quiz? Questions on the quiz? Okay, so let's talk. So I gave you the preview in the quiz. Hydrostatic force. Again, the goal of going through all these different kinds of problems is that we're building a toolbox then to solve, that you should be able to solve problems that you've not seen before, and that's the exam will be like that. Okay, the exam I'm gonna throw at you a whole new context, but you have, by going through all these different types that we've gone through, you will have the tools to do it if you've picked up on the big ideas. Okay. So hydrostatic force, we said this, total force on some region is going to be the sum of many forces, little forces. So by R, I mean like a region submerged in a fluid. Why does, or in what way will the force vary under liquid, underwater? Say so underwater. Why does the force vary underwater? How does it vary underwater? She said the force is going to be bigger, lower. How is that? Yeah.
It's going to be based on the density of the object compared to the density of water or whatever liquid is submerged.
No, so it's not going to matter what the thing is. We're just talking about how much force is against that thing. So it won't have to do with the density of if it's a plate or a piece of rubber or whatever under the water. But it has to do with, yeah.
How far down you are.
How far down you are. That's what, same thing. Yeah, they're right. Yeah, go ahead. Yeah, right. So I'll say that. Depth, right? So the deeper you are underwater, what happens with the force? goes up, right? So the deeper you go down, the force is going to intensify, or get greater. So if you have like a vertical something, a metal plate or anything, an object, the force is going to vary. It's going to get greater as you move down whatever surface or whatever region you're talking about. So that's why we're going to need this principle again. Okay, so pressure. The reason force varies with depth is because pressure varies with depth, first of all. So pressure on R varies with depth. So pressure, and this is what she was talking about. So the weight density of the fluid is important. The heavier the fluid is per unit is going to create, it's going to create more pressure because it's like you're sitting under something heavier, right? If you're under a more dense fluid, then there's more weight coming down on top of you. So that weight density isn't going to be in newtons per meters cubed or pounds per foot cubed. That's of the liquid. Times how far down you are gives the amount of pressure at that depth.
Mark, are you recording?
Yes, I am. Thank you. Okay? All right, so that's our pressure. And then to get force, so this is the pressure equation. Weight density is Greek rho. It's kind of like a P, and then you often see it with like a curly Q like this. So Greek rho is weight density of the fluid that we're in times the depth, d, gives the pressure at that depth. So what will the units of pressure be? What will the units of pressure be if we're saying newtons per meters cubed times meters? It'll be newtons per meter squared. That's pressure. Or pounds per foot square. That's your pressure unit. So how will we get force then? How will we get force? So force then will be pressure, what? What will we multiply pressure by to get force? What kind of quantity? No, we got pressure is newtons per meter squared. Area, right? So force is going to be then pressure times area, or P times A.
Force is just
Right. Or pounds. Force is newtons or pounds. That's right. Okay, but as soon as you move down a little bit, the pressure changes, so the force changes. As soon as you move down a little bit, the pressure changes. So again, just like with the work problems, we need some element for which we can calculate a little bit of force that doesn't change. So what kind of element are we going to have? What kind of geometric element are we going to have so that we can actually calculate an amount of force, like considering the pressure to be constant? What will our elements be like? We need pressure to essentially be constant so we can actually calculate a typical amount of force. How is that possible then? If pressure is varying with depth, how can we get a constant amount? Yeah. Right, he's going like this with his hand, right? We got to stay at the same depth in our elements so that the pressure stays the same and we can actually get a little bit of force. So that's right, some kind of horizontal strip is going to have, we can consider a constant pressure if that thing is narrow enough, and we can calculate a little bit of force, okay? So here is, let's do this. We got all the tools, let's do it. So there's some triangular plate like this. It's 8 meters this way. It's 4 meters this way. And the top of it's 5 meters from the surface. and this is water. So what was our density of water? Recall? 1,000 kilograms per meters cubed, or 60, was it 0.4 or 0.5?
5.
I gave you 5. Pounds per foot cubed. Remember that 1,000 is mass density. The 62.5 is weight density. So take that into account. Which one are you going to use? What do you need to do in this case? So what I want to do is I gave you the basic setup. We know that. So first of all, use always for these hydrostatic force. I think it's easiest to use your reference at the top, the water surface, okay? Or whatever the fluid surface is. Use that as your reference. X going down from there. Okay? The general idea is that the force is going to be the sum of all the little forces. And our typical, what's our typical little element going to be again on this plate? Typical element, something for which we can calculate a little bit of force. Pressure doesn't vary. Vertical, horizontal. So, a typical horizontal strip. We can actually calculate a constant amount of force for that. You've got all the tools. And on the exam, you have to kind of, and I've even given you a lot of help here setting it up. On the exam, you've got to take something new and run with it. So see if you can do it. Work together, get help if you need help. You've got all the tools. We've got the general idea of these types of problems. Should be able to do it. Okay, how did it go? How did it go? Not even close? Okay, but it's everything we've done, right? It's everything just with some new formulas for force and pressure. But it's everything else we've done. Linear relationship that gives you the width of your strip as a function of x or in terms of x. Set up your ordered pair, write the linear relationship. Why? Because as soon as you move down a little bit, that width changes. So your area is just going to be that width in terms of x times a little change in x. That's your area. Your pressure is the rho times depth. In this case, we're in metric, so we take the kilograms. We need to multiply by the 9.8 to get newtons. So we got the newtons per meters cubed times the depth gives us our pressure in newtons per meter squared times the little strip of area. And then we're going to add them all up. From what to what? 5, starting at depth 5 to 13. Any questions? These should be all beginning to feel alike, even though it's a different context. All the things we applied here, we've done before, just with a new, like I said, with a new formula. The force is pressure times area, and pressure is density times depth. Questions? Okay. Exam is Friday. Important web work for Wednesday. A little bit longer. You need to practice. Okay? Web work for Wednesday. Come on up. The exam 2 review outline is posted on Blackboard. Okay?
Is there recitation?
Yes, recitation this week for sure.
All right, so a couple of questions. Why would the slope be -2?
Change in dependent. So you want W in terms of X. Your dependent is W, that's like Y, right? And X is your independent. So the rate of change is the change in dependent over the change in independent. So change in W over change in X. You want W in terms of X.
The depth is changing. Okay.
You want W in terms of X. Your rate of change is change in W over change in X. So it's negative half.
Got it. And my other question, maybe if we get into three-dimensional objects underneath the water, would you take into consideration the force on all sides of the object? Because right now it's just like a two-dimensional.
Right. No, this is just the force, say, pushing on the liquid, say, by the liquid, just like from this side and that side. Right.
Like there's no others. We wouldn't times it by 2, like if there was like water on the other side of the object.
That's right.
Right. Okay.
That's right. Yeah. You're just thinking about just pushing on one side. So it's equal and opposite force, right? So pushing on the other side would be the same force. That's why it doesn't move.
Makes sense.
Equal and opposite force. So we just want one of them. Question? Yeah, sure.
Yeah, so like he's trying to find these two.
Just one side.
So he's trying
We do one side because there's going to be a force on the one side, and then equal and opposite force on the other side. We only want one of them. So if there was just force on one side, it would move. So you have the force on the one side and equal and opposite force on the other. So we're just calculating one of those. Does that answer it? Okay.